Hello there, everyone. Today, our group are going to choose the topic of ambulance. The situation that we are going to choose is ambulance accidents. From this incident, we are going to elaborate and explain the three LOs that we are going to obtain after we completing this course. Apart from that, we are going to give some insight from a biomedical student view in providing solution and improvement toward the problem itself. So let's dive into the LO first.
Hello, my name is Daniel Ashraf. I'm going to talk about the learning outcome number 1. So in this scenario, there is two phases, which is along a straight road and a curve road here. So the assumptions is the initial velocity, which is we use 90 km/h, acceleration negative 2.5 meter second squared, and the time from point A to point B is 25 seconds. So first we need to find the distance. Here we use the equation. After we replace it, we got 45 meter, and then using the answer, we use this equation to get the velocity at point B before it reaches point B. So moving on to the second phase, which is curve road. There's a little difference because there's a centrifugal acceleration. So we assume that the radius is 50 meter, mu 0.7, velocity using the answer before this, and the gravitational force 9.81 meter second squared. And then we use those numbers to calculate the maximum safe velocity using F greater than mv squared over r. This is because if the ambulance exceed the maximum speed, the ambulance will slip out. And then after replace the numbers, we get the velocity is 18.53 meter per second. And then we calculate the centrifugal acceleration of the ambulance using the equation AC equals to v squared over r. After we replace the numbers, we got the acceleration 8 meters second squared.
Hello, my name is Muhammad Hafiquddin, and I'm going to explain about the LO2, the solve problem for accelerating rigid bodies in two-dimensional. Start with the free body diagram. For the straight road position, we have normal and weight in the y direction, and we have a forward force and a friction force for the horizontal force. We assume that the mass of the ambulance is 1770 kg, and the coefficient is 0.7, acceleration is minus 2.5, and using this formula, we can find the forward force, and after plug in all the value, we can determine that the forward force is 7729.59. So we can say that the ambulance is moved forward. For the curved side road, the FBD is shown as this. We have a centripetal force, and we have the centrifugal force, and we have the weight and the normal force. We can find the centrifugal force by using this formula, mv squared over r, and plug in all the value, and we can get 14160 for the centrifugal force. And for the centripetal force, we can determine the value by using this formula, mu times n, where is the mu is 0.7 and n is the normal force, and we can determine that the value is 12154.6. And for the net force, which is the centrifugal minus centripetal force, and we can get the net force is 2005.4 moving toward the centrifugal force. This will actually cause the ambulance to slide off. Moving on to the kinetic diagram. For the straight road, the F equal to MA is in direction of the moving ambulance. If the ambulance is moving to the right side, mean that the net force will be moving in the same direction. And for the curve side, we can see that the net force is moving in this direction, causing the ambulance to slide off.
Hi guys, my name is Afif. Let's continue to the LO3, which is to analyze the kinematics and kinetics of the particles.
Alright, for the LO3, we will do rolling motion analysis at the Toyota Hiace ambulance tire. So here we have the rolling tire. So we can see here the point G and the point A. The point G is the center of the gravity of the tire, and the point A is the point where the tire touches the ground. From the previous LO, we can understand that the cause of the accident is because of the centrifugal force is more than the centripetal force. The centrifugal force pulls the ambulance to the right of the road, and it doesn't because of the slipping. So there is no slip occurs. Okay, here we can make the equation. The VG equals to the VA plus the RGA, the R from G to A, times with omega. Since there is no slip occurs, the V of A, we can put it as 0. Okay, here we put the VG equals to 20 meter per second because we choose the velocity of the ambulance at the point B. And this value of 20 meter per second we obtained from the previous LO. The R is 0.3276 meter. This radius is from the real measurement that we found from the online sources. So from this, we can calculate the omega, the angular velocity equals to 61.05 rad per second. We have calculated the angular velocity. How about the angular acceleration? So just use the formula, the AG equals to alpha R. The AG is the acceleration of point G equals to the acceleration, the angular acceleration times with the radius. So here we put the AG equals to negative 2 meter per second squared because the acceleration of the ambulance at the point B is equals to negative 2 meter per second squared. And the R, the real measurement here. And we can calculate the alpha equals to negative 0.1638 rad per second squared. The negative indicates that it is decelerating. As the ambulance decelerates, the angular acceleration of the tires also decelerate. Okay, we can also calculate the acceleration of the point A. The acceleration of point A equals to omega squared times with R, and the direction is toward upwards. Why is it towards upward? Okay, let's understand. Before the point A touches the ground, the velocity of the point A is directed downward. But after it touches the ground, the velocity is going upward. Therefore, the point A accelerates upward as it leaves the ground. So here we put the omega, what we have calculated just now, 61.05 rad per second squared, and times with the radius. We get 20 meter per second squared. So let's recap what we have calculated just now. The omega, the angular velocity equals to 61.05 rad per second. The angular acceleration, the alpha equals to negative 0.1638 rad per second squared. The negative indicates that it is decelerating, and the acceleration of the point A equals to 20 meter per second squared, and the direction is going upward. So that's all for the LO3. Thank you.
Okay, now we are going to talk about the solution and the improvement that can be done to prevent or to improve the condition of the incident itself. So, as you guys know, accidents do occur anytime and anywhere, and anyone can happen to it. So, we as a biomedical engineer need to provide a safety precaution for the passenger, the patient, and the driver of the ambulance. So, from what I see, they have a strapping gear devices, which is the tali pinggang keleda, on their seat. That is good but there are some improvement that can be done to ensure increase of security toward all of them. So this is a few suggestions that can be considered in providing a new model of the strap gear. The first modification that I would like to suggest is to adding a new additional layer of a shock absorber. This is because when the accident occurs, a large force of impact will occur toward the body, and the first layer that be happening is our strap. So supposedly, with the additional layer of the shock absorber, it will absorb the shock and reduce the pressure exerted toward the body itself. So the pressure exerted less, the less painful it is. So this will overall give an additional protection toward all of the passenger, the patient, and the driver itself, thus reducing the casualty of the arm. So for the second one, the modification that I can see that can be done is the strapping gear for the patient on the gurney itself. We should put a shoulder pad. This is because during the accident, when the vehicle is leaving off the course of the road, the patient will experience a large exerted pressure on their shoulder, because the only thing that have there is a strap, which is a very small surface area which provide a large force exerted to the body. So the thing that is, we can provide a shoulder pad that ultimately give protection and also giving less pressure exerted toward it when the vehicle off course from the road. So that is the few modification that I can suggest it from our student view as a biomedical engineer student. I hope this will give a new sight toward a new model for safety strap gear for the future generation.